You've heard it 1,000 times, Moon, then Mars, then the rest of the solar system. But what if that roadmap is wrong? And our first real off-world city shouldn't be on Mars at all, but on a frozen moon almost 1 billion kilometers away. In this video, we're going to stack Mars against Titan. Radiation, gravity, atmosphere, resources, and ask a hard question. Are we aiming humanity's first true colony at the wrong world? Mars orbits at about 1.5 times Earth's distance from the Sun, around 225 million kilometers, about 140 million miles. Titan, which orbits Saturn, is way out at roughly 9.5 times Earth's distance, around 1.4 billion kilometers, about 870 million miles. On a basic distance chart, Mars looks cheaper, faster, safer. But distance is not what kills you first in space. The real limit is, can you keep humans alive for years without insane levels of engineering overhead? And here the story flips. Mars has a surface pressure of around 600 pascals. That's less than 1% of Earth's sea level air. Titan sits at roughly 1.5 bar, about 50% more than Earth, under an atmosphere that is almost all nitrogen, just like here. Mars is basically a controlled vacuum. Titan is already at a pressure that human technology can work with easily. So the quiet question nobody puts on the big posters is simple. Would you rather build your first real city inside a world that's trying to rip every building apart from the inside? Or on a world where the outside air actually helps your structures instead of fighting them? You keep hearing that Mars is almost Earth-like, but how true is that once you strip away the slogans? Yes, Mars has gravity, about 0.38 g, which is better than 0 g. Yes, the Martian day is close to 24 hours. But those are small wins compared to the rest of the environment. Mars is bitterly cold, average surface temperature around -63 degrees Celsius. That's about -81 Fahrenheit. The air is dry, the surface is blasted by radiation, and the sky is too thin to protect you from high-energy particles from space. Titan is much colder, around 94 Kelvin, about -179 Celsius, -290 Fahrenheit, so you need serious insulation and heating, no question. But once you step outside, you're standing in thick, slow air that actually absorbs radiation for you. On Mars, you step into almost vacuum, so your body's suit is a rigid pressure shell, your habitat is a balloon pushing outward all the time, and every leak is a life-threatening emergency. On Titan, the outside pressure is close enough to human comfort that your engineering job is mainly to keep heat in and toxic gases out, not to hold back space itself. So the Earth-like label hides the real situation. Mars looks slightly familiar in photos, red rocks, blue sky, dust, so our brains relax. But functionally, it's a cold, irradiated, low-pressure desert. Titan looks alien in pictures, orange haze, dark ground, so we dismiss it, even though the physics there are actually more helpful for long-term survival. That raises the next question. Is Titan just a nice theory on paper, or do we actually have solid measured data that proves it's buildable? We do, and that's where the Cassini-Huygens mission quietly rewrote the playbook. On January 14th, 2005, the Huygens probe dropped through Titan's atmosphere for more than 2 hours. It didn't guess, it measured. It recorded pressure climbing to roughly 1.5 bar at the surface. It sampled a nitrogen-rich atmosphere with methane mixed in. It felt real winds. It sent back images of channels and branching patterns that looked like river valleys carved into solid ice. When Huygens hit the ground, the surface was firm enough to support it. It did not sink into some bottomless sludge. It landed, sat there, and kept transmitting. Meanwhile, Cassini orbited Saturn and used radar to see through Titan's thick haze. It mapped lakes and seas of liquid methane and ethane near the poles, some hundreds of kilometers, hundreds of miles across. It measured temperatures, tracked seasonal changes, studied the haze and cloud layers. So today, Titan is not an unknown sketch. It is a world with real topographic maps, real climate data, and real surface chemistry. That means when we talk about building a base on Titan, we are not daydreaming. We're working off a data set. We know the air pressure. We know the basic composition of the atmosphere. We know there are stable liquid bodies on the surface. we know the gravity, we know there is water ice under the organic layer. So now the issue is not, is Titan real? It's, what happens to our entire expansion plan if we ignore this place and go Mars first anyway? You only get a few chances to spend multi-trillion-dollar budgets on new worlds, so picking wrong is not a small mistake, it's a huge strategic risk. Think about what a Mars-first choice forces you to do. From day one, every habitat has to deal with intense radiation from cosmic rays and solar storms. To keep long-term doses down, you need meters, yards of soil or rock piled over living spaces, or you dig deep underground. That requires heavy machinery, power and time, all before you've even set up real industry. The atmosphere is mostly carbon dioxide at very low pressure, so your life support has to constantly scrub CO2, recycle water, and maintain high internal pressure while the outside tries to pull it apart. Dust gets into everything, grinding seals, scratching visors, clogging filters. On Titan, the built-in environment removes some of those biggest headaches. The thick nitrogen atmosphere gives you a constant planet-scale radiation shield. The pressure is high enough that your habitats can be close to neutral pressure with the outside, under slight compression instead of violent tension. The surface has hydrocarbons for fuel and chemistry, and enormous amounts of water ice for oxygen and drinking water. Instead of spending most of your early decades just defending against radiation and vacuum, you can spend more effort building power systems, factories, and transport networks. So going Mars first locks us into a long period where we are just surviving. Going Titan first lets us move faster towards scaling up. That leads to the key strategic question: is Titan just another cool place, or is it actually the best way to unlock the whole solar system, including Mars? Here's the core idea: Titan is not just a target, it's a leverage point. Because the sunlight out at Saturn is weak, Titan forces you away from giant solar farms and toward nuclear power from the start. That sounds harsh, but it's exactly what we need for every future base beyond Mars anyway. Titan's cold environment and constant access to water ice make it an ideal training ground for running compact fission reactors, managing waste heat and keeping closed life support systems going for years. You learn how to build reactors that can operate for decades without constant maintenance teams flying in from Earth. The low gravity, about 0.14 g, and the dense air make heavy lifting and transport much easier. With the right aircraft and ground vehicles, you can move large structures, tanks, and mining equipment with far less energy than on Mars or Earth. The huge supply of hydrocarbons and nitrogen gives you feedstock for plastics, fuels, fertilizers, and advanced chemicals. Over time, that combination, power plus raw materials plus easy transport, adds up to real off-world heavy industry, not just small research stations. Once you can do that on Titan, you have solved most of the hard parts of long-term space living. Running a Mars base at that point becomes less of a desperate experiment and more of a normal, if still challenging, expansion step inward. Shorter travel time, stronger sunlight, faster communications all become bonuses instead of lifelines. So the uncomfortable question is this: if the place that is farther away actually makes us stronger, faster, and more capable everywhere else, including on Mars, are we making a mistake by following the simple closer first instinct and ignoring the deeper physics? You'd think the last place to look for friendly air is a moon, almost 1 billion kilometers from the sun. So why does Titan actually give you an atmosphere you can work with, while Mars basically gives you nothing? Start with pressure, because that's the part nobody talks about in the posters. On Titan, the air at the surface pushes at about 1.5 bar. In simple terms, that's like being under roughly 5 to 10 meters of water on Earth, around 15 to 30 feet. Your body can't handle that directly because the air is methane-rich and way too cold, but your hardware loves it. On Mars, surface pressure is around 0.6% of Earth's, way under 1%. That means every Martian habitat is trying to balloon outward all the time. The inside pressure is way higher than the outside, and every wall, every joint, every window is under constant stress. One bad weld, one micro crack, and your air wants to rush out into space. On Titan, your structures sit almost in balance with the outside. You keep the inside slightly different from the outside pressure, but your walls sit in gentle compression, not violent tension. That's safer, cheaper, and easier to scale up. Now add density. Titan's air is about 3 to 4 times denser than Earth's air at sea level, roughly 4.5 kilograms per cubic meter. When you walk through a sauna through it, it would feel thick and heavy, more like moving through slow water than through thin, high mountain air. That sounds annoying for walking, but in engineering terms, it's gold. Dense air carries heat well, so heat from your reactors and habitats spreads more evenly. It damps out sudden temperature swings. It gives you aerodynamic control for aircraft and parachutes. Mars, by contrast, has air so thin that even big parachutes barely work, and the atmosphere carries very little heat, so the surface sees brutal shifts. So you have this thick, heavy blanket of air on Titan, holding your structures together and giving you real leverage. And that leads straight into the next hard question. If the air is that strong, can it actually shut down the worst killer in deep space, radiation? Radiation is the slow, invisible enemy. On Mars, you stand on the surface under a thin atmosphere with no strong global magnetic field. Measurements suggest astronauts could take in something like 0.2 to 0.7 millisieverts per day on the ground. Stretch that over a full mission, and you're talking hundreds of chest x-rays per year, sometimes more. That's long-term cancer risk, heart problems, damage to the nervous system. To fight that, Mars bases almost have to go underground or pile meters, yards of soil over every living area. Titan attacks that problem before you even start building. A 1.5 bar column of nitrogen overhead acts like a constant shield, similar in effect to walking around under several centimeters, a few inches of solid metal spread over your whole body all the time. Saturn's magnetic environment adds partial protection against some charged particles. Then on top of that, you have local ice and rock, a single meter, about 3 feet of Titan ice around or above your habitat, adds a huge amount of extra shielding. Enough that your long-term radiation levels can get close to what airline crews or people at high altitude on Earth experience. You don't have to bury entire cities just to get started. You can build on the surface and then thicken the walls and roofs over time using local material. So Titan's atmosphere shields you from space in a way Mars simply can't. But that thick air also changes the hardest moment of any mission, the landing. So the next question is, does Titan also solve the nightmare of dropping heavy stuff onto another world? Landing big masses on Mars is a balancing act with physics that really doesn't like you. The air is too thin to slow a large, heavy spacecraft with parachutes alone, but still thick enough to heat you up violently if you come in fast. That's why you hear phrases like 7 minutes of terror. To get rovers like Curiosity and Perseverance down, engineers had to combine heat shields, supersonic parachutes, powered descent, and even a sky crane that lowered the rover on cables. Now scale that up to multi-ton habitats and reactors, and the difficulty goes way up. Titan flips this. Its dense atmosphere means classic blunt heat shields work very well at killing speed high up, without insane heating rates. Parachutes become powerful again. The Huygens probe basically rode parachutes all the way down, only using small thrusters for orientation. For big cargo, you can do a simple stack, a heat shield to survive entry, a set of large parachutes or steerable parafoils to slow and guide, then maybe a short burst of retro rockets in the last few hundred meters to land softly. The atmosphere does most of the hard work. Every kilogram of retro propulsion hardware you don't need is another kilogram of life support gear, scientific instruments or construction equipment you can bring instead. So Titan's air helps you land, helps you survive, and helps your structures, but it's not just air to push against, it's also raw chemical inventory. That brings up the next key question. If almost all that gas is nitrogen, what can you actually do with it? Titan's atmosphere is about 98% nitrogen. That's surprisingly close to Earth, where nitrogen is around 78%, the rest mainly being oxygen and a bit of other gases. Nitrogen sounds boring, but it's one of the main building blocks for life in industry. You need nitrogen compounds in fertilizers to grow crops, You use nitrogen in a lot of industrial processes, from making explosives to manufacturing plastics and other chemicals. On Mars, by contrast, the air is mostly carbon dioxide and nitrogen is only a tiny trace. That means any serious Martian agriculture has to hunt hard for nitrogen sources, dig it out of the soil or import it from elsewhere. On Titan, you start with an atmosphere that's already a giant nitrogen reservoir. Split water ice into hydrogen and oxygen using power from your reactors, combine the nitrogen from the air with hydrogen, and you make ammonia. From ammonia, you get nitrates for fertilizer and a whole family of industrial chemicals. Take nitrogen and mix it into different organic molecules, and you build everything from simple solvents to complex polymers. In metric terms, per square meter of surface, Titan's atmosphere holds roughly 10 times as much mass as Earth's. In simple terms, it's like living under a permanent planet-scale high-pressure tank, full of free feedstock. So the air keeps you safe and feeds your chemistry, but it also becomes the medium your whole base talks and moves through. That sets up the next question. If the sky itself is this thick, how does that change communication and movement for a Titan colony? Dense air changes how radio waves and sound travel. Lower frequency radio signals can go a long way close to the surface, bending with the curvature of the world. Balloons, airships and drones can stay afloat with very little power, because the atmosphere gives a lot of lift for a small volume of gas or a small wing. That means your communication infrastructure doesn't have to be a network of tall towers drilled into rock. It can be a web of floating platforms a few hundred meters up, say around 1,000 feet. Each one carries antennas, maybe cameras and sensors, and together they form a high bandwidth mesh over a huge area. Compare that to Mars, where dust storms can weaken or block some links, and the thin air makes balloons almost useless. On Titan, your base uses the atmosphere like a highway, and like a fibre optic cable at the same time. Data, supplies, and people can move by air cheaply and reliably. You don't just survive under the sky, you exploit it. So you've got pressure that works with you, not against you. A built-in radiation shield, easier landings, a whole chemical industry floating above your head, and a sky that turns into your transport and comms network. But all of that still leaves a deeper issue hanging. If Titan's environment is that helpful, what does that mean for how long human bodies can actually live out there compared to a place like Mars? Start with the uncomfortable question. How long could a human body realistically last on Mars before radiation quietly wins? We already have a rough benchmark, the International Space Station. Astronauts in low Earth orbit pick up roughly 0.5 to 1 millisievert of radiation per day, even though they're still partly inside Earth's magnetic field. That dose adds it's up fast. Over 6 months they can hit around 100 millisieverts, and space agencies already treat that as a serious number. Now shift to Mars. On the surface, with almost no magnetic field and a very thin atmosphere, measurements suggest daily doses that can be in the same ballpark or worse than the station, but now you're talking about people living there for years, not months. A 500-day stay, which is a realistic mission length, can easily push you past 250 millisieverts or more, and that is just the start if you plan to stay for multiple rotations or for life. Every extra dose slowly raises your risk of cancer, heart disease, and other long-term problems. DNA damage accumulates. Your body can repair some of it, but not all, especially when you get hit day after day. The standard answer is, we'll shield it, but that means real mass. To cut the dose to something closer to what you get on Earth, you need meters, yards, of Martian soil or rock over your head, or thick tanks of water around your living spaces. And you need that early before you have big machines, strong power systems, and full factories. So your very first crews on Mars face a race. Can they build a proper bunker before years of radiation stack up inside their bodies? So if Mars forces you into that race with biology right away, what does Titan do to that picture? Titan changes the whole starting point. First, it sits far from the sun, so the intensity of solar particles is already much lower. Second, that thick nitrogen atmosphere at about 1.5 bar acts like a permanent shield overhead. High-energy cosmic rays and solar particles have to plough through a lot of gas before they ever touch the ground. Models suggest that the radiation dose at Titan's surface could actually be lower than what you get on long, high-altitude airplane flights on Earth. That is a completely different regime from Mars. Now, base design flips. On Mars, the first question is, how deep do we need to bury this to not fry ourselves over a lifetime? On Titan, the first question becomes, how big can we safely build above ground before we even bother to go underground? You are not spending your early years hiding from invisible bullets out of the sky. You are mostly fighting cold. That does not mean zero shielding, but it means the level of emergency is lower, and you can take more time to add extra protection in a planned industrial way instead of in a desperate scramble. But shielding still matters, so the next issue is, how hard is it to get the mass you need in each place, and what does that do to your rockets? Think about what proper shielding looks like in raw numbers. To bring radiation down to comfortable long-term levels, you might want on the order of a few grams of material over every square centimetre of your habitat surface. Translate that into simpler units, and you end up needing around 50 kilograms of stuff over every square metre, roughly 10 pounds per square foot or more. If you try to launch that from Earth as metal plates or water tanks, your mass budget explodes. A single medium-sized habitat might need tens or hundreds of tons of extra shielding. That means more launches, more fuel, more money, all to ship material whose only job is to sit there and absorb particles. On Titan, you just look down. Every cubic metre of local water ice weighs around 900 kilograms, about 2,000 pounds. And that ice is a perfect shield, made of light elements that are very good at slowing and stopping cosmic rays. If you stack just 1 metre, around 3 feet of ice over the roof of a habitat, you suddenly jump from the bare minimum shielding to an extremely thick protective layer. In shielding terms, that is like going from a thin jacket to a full bunker. You did not launch any of it from Earth. You scooped it from the ground with local equipment. The cost is energy and time on site, not lift capacity from home. So Titan gives you an environment where the outside air already does most of the job, and the remaining shielding mass is basically free. But that still leaves the deeper issue. How does this play with human lifetimes, children, and multiple generations? If you pick a high radiation world like Mars for your first real colony, you're committing to a long, unequal fight with biology. Adults who move there in their 30s or 40s will spend the rest of their lives under higher-than-Earth doses, which means every decade brings more risk. Children born there will grow up in that environment from day one. Even if you shield your main habitats, every trip outside, every drive in a rover, every construction job under the open sky adds small hits. Over many years, that can stack into real health effects that are hard to predict and almost impossible to roll back. On Titan, the baseline is much kinder. The natural environment is cold and airless in terms of oxygen, but it is not radiologically aggressive. That means you can align your engineering timescale with human lifespans. You can plan for people to live there for 40, 50, 60 years without getting doses that make them long-term test subjects. You can run outdoor work in proper suits without treating every excursion like a dangerous medical procedure. You can talk seriously about families and children in a way that does not sound reckless. Titan starts to look less like a remote outpost and more like a place where a community could actually stay, grow old, and pass on knowledge. And once you see that, it hits the master plan directly, because if your first off-world city is supposed to last for centuries, radiation is not a side note. It is the central filter. So how does that change the Mars first logic everyone repeats? If you add everything up, Titan does not just edge out Mars on radiation, it crushes it. Mars demands thick artificial shielding, deep burrows, heavy structures, and it demands them early, when you are weakest. Titan hands you a thick nitrogen layer in the sky, and massive amounts of water ice on the ground, that together give you an almost Earth-like safety margin if you design smart. On Mars, you spend huge effort recreating what Titan gives you as a starting point. For a species planning its very first permanent city off Earth, that difference is brutal. One option forces you into a constant, expensive struggle to beat radiation enough that people can just live a normal span. The other option reduces radiation to a manageable, almost background problem, so you can focus on power, industry, and scaling up. When you see it that way, the choice is not just about which world looks cooler, it is about which world lets your grandchildren still be healthy under alien skies. So if Titan makes human lifetimes and even multi-generation life realistically safe, while Mars keeps you on a knife edge, why would you ever pick the harder? Harsher option first, unless you have also misunderstood something else just as important: the gravity your body has to live in every single minute. Radiation is one threat, but there's another thing your body can't ever escape: the pull of gravity. So which gravity experiment do you actually want to run on yourself and your kids? On Earth, your whole biology is tuned to about 1g. That's an acceleration of roughly 9.8 meters per second squared, around 32 feet per second squared. Your heart, your bones, your muscles, your inner ear, all of it was built around that constant load. Mars offers about 0.38 g, roughly 3.7 meters per second squared. Titan sits even lower, around 0.14 g, about 1.35 meters per second squared. We know what happens in 0g on the space station. It is ugly. Without heavy exercise, astronauts lose 1 to 2% of their bone mass every month. Muscles shrink, the heart deconditions, balance systems get weird. But here's the key point. We have almost no real data on 0.38g or 0.14g. No one has lived for years at those levels. Both Mars and Titan are untested on the medical side. From a health standpoint, you could argue that Mars, being closer to Earth's gravity, might be better. From an engineering standpoint, lower gravity is raw advantage. It changes what you can lift, how big you can build, how hard it is to launch things to orbit. So the question is, do you pick the place that might be a bit closer to Earth biology, or the place where gravity becomes a tool you can use almost everywhere? Think about what 0.14g actually feels like in practice, because it is more extreme than the numbers sound. On Titan, your weight drops to about 1/7 of what it is on Earth. If you're 70 kilograms, about 155 pounds, you weigh the equivalent of 10 kilograms, around 22 pounds. You don't become lighter in mass, you still have the same inertia, but every step you take pushes you down far less. In a proper insulated pressure suit, you could jump several meters high, several yards without much effort. Walking becomes easy, slopes feel milder, and if you trip, you hit the ground slowly compared to Earth. Now apply that to work. A machine that weighs 1 ton on Earth, about 2,000 to 200 pounds, effectively feels like around 140 kilograms, roughly 300 pounds on Titan. 2 or 3 people, plus some basic lifting tools, can move things that would absolutely require cranes back home. Early construction, habitat assembly, reactor installation, all of that goes faster because gravity is barely fighting you. On Mars, 0.38g, you still feel more than a third of your Earth weight. That's a relief compared to 1g, and it's probably better for your muscles and bones, but it doesn't give you the same brute mechanical advantage. Heavy gear is still heavy. You still need large cranes and powerful vehicles to move the big pieces. So in Titan's gravity, human bodies and small robots get a hidden upgrade in raw lifting ability, and that feeds straight into your next problem, the size and cost of the structures you have to build. So how different does civil engineering look when gravity barely pulls on your buildings? Take a 100-ton habitat shell. That's 100,000 kilograms, about 220,000 pounds of structure. On Earth, that mass presses straight down with full 1g, so every column, every foundation has to be seized to support that load plus safety margins. On Titan, the same 100-ton shell weighs the equivalent of about 14 tons back on Earth, roughly 30,000 pounds. That's like comparing a loaded semi-truck to a small bus. Your walls can be thinner. Your supports can be smaller. You can throw up 50-meter masts, about 160 feet for antennas or power lines without massive concrete blocks at the bottom. Radiation berms, big walls of ice and regolith around a base, can be piled higher with less risk of collapse. Less structural weight means less material you have to launch from Earth and less material you have to dig locally. That shrinks your supply chains and your timelines. On Mars, 0.38G still drags on everything hard enough that your engineering, while a bit lighter than on Earth, still looks very similar. Heavy beams, serious foundations, tall structures that need careful bracing. Titan lets you cheat more, and in the early years of a colony, those cheats are the difference between slowly putting up a small camp and rapidly assembling a full town. But low gravity is not just a gift, it might also be a health risk. And this is where Titan becomes interesting as a scientific tool, not just an easy building site. So the next question is, how do you actually find out what 0.14G does to a human body without rolling the dice blindly on a whole population? We really do not know if 0.14G is enough to keep bones and muscles healthy over decades. It might be fine with some exercise, or it might behave closer to microgravity, where the body slowly degrades unless you spend hours a day on machines. But that unknown is exactly why Titan is useful. Remember, Titan already solves most of the radiation problem with its air and distance. That means you can study low gravity effects without radiation confusing all your data. Inside a Titan base, you can build rotating habitats, small centrifuges, where people spend part of their day or sleep cycles at higher effective gravity, maybe 0.38G like Mars, or even 1G like Earth. Then they go back to working in 0.14G outside or in normal rooms. Doctors can track blood flow, bone density, muscle mass, balance over years. They can compare people who spend different amounts of time in higher gravity sections. If we go Mars first, we don't get that clean experiment. On Mars, low gravity, radiation, dust exposure and isolation all hit at once. When health problems show up, you don't know which factor is driving what. So Titan gives you a controlled lab for human gravity biology, while still letting you run a real city. But gravity is not just about walking and bone health, it's also about rockets, and about how expensive it is to connect your base to the rest of the solar system. So how much does Titan's low pull actually save you when you start launching things? To leave any world, you have to reach a certain speed, the escape velocity. For Earth, that's about 11.2 kilometers per second, roughly 7 miles per second. For Mars, it's about 5 kilometers per second, around 3.1 miles per second. For Titan, it's only about 2.6 kilometers per second, roughly 1.6 miles per second. That gap is huge. Rocket design is all about how much propellant you need to get to a target speed. When the required speed drops, the fraction of your vehicle that can be payload instead of fuel goes up sharply. On Titan, you can loft cargo into orbit with relatively small rockets, powered maybe by local methane and imported or locally produced oxygen. The tanks are smaller, the engines are simpler, and the same launch pad can send up many flights over time without consuming insane resources. That's exactly what you want if your goal is to build fuel depots, assemble big ships in orbit, or export products to other moons and planets. Low gravity also means that you can experiment with non-rocket launch systems more easily, like electromagnetic launch rails or high-altitude balloon-assisted stages, because the stresses on hardware are lower. So when you stack it up, Titan's gravity regime gives you easier construction, easier lifting, a clean testbed for human health in low G, and cheaper access to space all at once. Mars gives you one possible health advantage, being closer to 1G but offers far less mechanical advantage and much more radiation trouble. For a civilization that needs both science data and raw industrial output, Titan's low gravity looks far more like a tool and far less like a problem. And that leads to the next pressure point. If gravity, radiation, and atmosphere all lean this hard toward Titan, why are we still pretending that a place with almost no usable sunlight, way out at Saturn, is too hard, when the real question we should be asking is whether we're ready to run serious power systems in that permanent twilight? On almost every world we've looked at, flying is hard or impossible. So why does Titan flip that and turn its entire sky into the easiest transportation layer in the solar system? Think about what makes an aircraft stay up. Lift mainly depends on 3 things: how dense the air is, how big your wings are, and how fast you move through that air. Titan gives you 2 huge advantages at once. Its air is several times denser than Earth's, and its gravity is only about 0.14G. That means you don't need big wings or high speed to make enough lift. Even a human-scale flyer starts to look realistic. With a wingspan of around 4 to 5 meters, say 13 to 16 feet, and leg and arm power like a strong cyclist, a person in a pressurized suit could, in principle, glide and even flap themselves into the air on Titan. You still need technology and safety gear, but the raw physics say this works. Now compare that to Mars. The Martian atmosphere is so thin that air density is less than 1% of Earth's at sea level. Helicopters like the Ingenuity drone need oversized rotors spinning very fast just to get a tiny payload off the ground. Scale that to human or cargo size and the challenge explodes. Titan is the opposite. It's the first place where normal-looking wings and rotors suddenly become overpowered. For a colony, that difference is huge. On most worlds, ground vehicles are your default. On Titan, flying becomes the normal choice. And this isn't just a thought experiment on a whiteboard. Space agencies are already building hardware to prove it. So the next question is, what happens to your whole strategy when your first real mission is not a rover, but a flying nuclear drone? NASA's Dragonfly mission is aimed straight at Titan. It's a rotorcraft, basically a big drone with multiple rotors, powered by a nuclear source. It's designed to land once, then take off again and again, flying from site to site over Titan's surface instead of crawling slowly like a rover. We're talking about a vehicle around the mass of a small car, near 1 ton, about 2,200 pounds, using Titan's dense air and low gravity to hop kilometers, miles, at a time. That is a totally different mode of exploration. On Mars, you design missions around slow, careful driving, because every meter costs power and time. On Titan, the same level of hardware can leap huge distances, land, sample, then lift again. The physics that allow Dragonfly to work also scale up. The same air and gravity that let a science drone fly, let you build cargo drones, crew transports, heavy lifters. In a Titan colony, your pickup truck is not a 6-wheeled rover grinding along at walking speed. It's a vertical takeoff and landing aircraft that cruises at highway speeds through thick, stable air. So now look at the big picture. Every early mission to Mars has crawled. So what happens when your Titan missions can cover the same distances in minutes that took Martian rovers years? Let's compare actual numbers. Sojourner, Spirit, Opportunity, Curiosity, Perseverance, all the Mars rovers measured their lifetime paths in tens of kilometers, tens of miles over spans of years. They stopped frequently, checked the ground, avoided hazards, conserved power. That's not because engineers are lazy, it's because the terrain is rough, the air is thin, and solar energy is limited. On Titan, a single mid-sized aircraft could fly tens of kilometers in one hop, then repeat that again and again inside a single Titan day, which is about 16 Earth days long. A fleet of drones could map hundreds of thousands of square kilometers, tens of thousands of square miles, in a few years, not in decades. They could sample shorelines of multiple methane lakes, scan mountain ranges of ice, survey potential base sites, all far faster than ground vehicles. For a new colony, that speed multiplier is critical. Science moves faster, but so do basic tasks like scouting safe landing zones, locating good ice deposits, or checking weather patterns. When you understand a whole region in detail early on, you avoid bad choices that might lock you into poor locations for decades. But exploration is only one side. Real colonies have accidents, and distance kills when you can't move fast. So you have to ask, what does it mean for safety when your main rescue and logistics tools have wings instead of wheels? On Mars, when something goes wrong, response options are slow. Dust storms can cut solar power for weeks, turning rovers into barely moving bricks. A vehicle breakdown can leave a crew stranded with limited shelter. To get help to them, you send another rover, which also crawls at a few kilometers per hour at best and often much less. Even with nuclear power, thin air and rough ground limit your speed and payload. On Titan, that same thick atmosphere that slows you a bit when you walk becomes your best ally once you put engines and rotors into it. A small aircraft with a compact nuclear power source or high-energy batteries can cruise at tens or even hundreds of kilometers per hour, tens of miles per hour, over terrain that would utterly stop a rover. If a remote outpost loses heat or air, you can dispatch a rescue craft, drop supplies or evacuate people in a single trip. If a vehicle breaks down, you send a replacement by air and maybe airlift the damaged unit back to base. The whole moon becomes accessible, not just the area within slow driving range. Logistics also change. Need to move reactor parts, habitat segments, food or mined materials between sites? On Mars, you build roads, or you accept that everything will move forever at rover speeds. On Titan, you set up aerial routes. Aircraft follow fixed paths using the dense atmosphere for stable flight, like airplanes using established corridors on Earth. Weather is slower and more predictable because of the thick air and low gravity, so scheduling is easier. The same physics that make rescue possible also make routine freight and passenger movement fast and reliable. So we're not just talking about a cool side feature. On Titan, the sky turns into your main highway system. That also feeds directly into how fast you can actually build up a base from scratch. So the next thing to get clear is, why does flight capability matter so much in the very first years of a settlement? Your first base is always fragile. It depends on a few key power systems, a few habitats, a limited number of experienced people. When you want to expand, you have to build new modules, lay out new lines, set up backup power, and push into new terrain for resources. On a world where you can only crawl on wheels, every expansion step is slow and risky. You think twice about placing a new outpost 50 kilometers away 30 miles, because supporting it is hard. On Titan, aircraft erase a lot of that friction. Need to build a new ice mining site 80 kilometers away? You scout it quickly from the air. You pre-position equipment by drone. You ferry crews back and forth daily if you want. You can even leave some facilities uncrewed for stretches, because you can still check on them regularly with flyovers. That lets your base grow like a network, with multiple nodes, not just one dense cluster surrounded by a dead zone. And the same systems that move cargo and people also carry sensors, cameras, mapping gear, and science instruments. So as you grow, you're constantly updating high-resolution maps of the surface, watching for changes in lakes, monitoring weather, and tracking any problems in your own infrastructure from the air. That situational awareness is something Mars will always struggle to match as long as it has to rely mostly on ground rovers. Put all of this together, and Titan stops looking like a frozen rock and starts looking like the first world where flying, not driving, is the default. That changes your risk profile, your growth speed, and your scientific return. But there's a catch sitting above all of this, one you can't dodge forever. All those aircraft, all those bases, all those life support systems, they need power, and out at Saturn, the sun is barely a weak lamp in the sky. So the next hard question is this: if Titan is the first place where the sky is easy, but the sunlight is almost gone, are we actually ready to run a whole civilization in deep cold on nuclear fire alone? Here's the catch nobody likes to talk about. Titan lives in almost permanent weak daylight. So how do you power a whole city in a place where the sun is barely brighter than a car headlight? Start with the raw sunlight numbers. At Earth's distance from the sun, you get roughly 1,360 watts of solar power hitting each square meter at the top of the atmosphere. Mars orbits farther out, so that number drops to around 600 watts per square meter. That's still workable, as the Mars rovers and landers show. Titan orbits with Saturn, about 9.5 times farther from the sun than Earth. Because sunlight drops off fast with distance, by the time you reach Titan, you only have around 15 watts per square meter at the top of the atmosphere. Then you slam that weak light through Titan's thick, hazy air, and only a portion makes it to the ground. In practice, a Titan solar panel might only give you tens of watts per square meter on a good day. To run even a modest settlement using only solar, you'd need square kilometers of panels, square miles, spread out on a freezing surface, kept clean and aligned, wired back to your base. That's insane amounts of hardware in one of the coldest places in the solar system. So Titan simply takes away the easy, comfortable answer, we'll just use lots of solar, and forces you straight into the serious option, high power nuclear from day one. That sounds heavy, but it actually lines up perfectly with what the outer solar system demands anyway. So the next hard question is, if fission isn't the backup but the default, does Titan actually make running nuclear reactors easier, not harder? A compact fission reactor is basically a very dense power plant. From a few tons of fuel and machinery, you can get megawatts of electricity for years. On Earth and Mars, reactors often have a waste heat problem. They produce more heat than you want, so you need big radiators and cooling systems to dump that energy into space or air. On Titan, that entire situation flips. The surface sits around minus 179 degrees Celsius, roughly minus 290 Fahrenheit. Heat is not a nuisance there, it is survival. Picture a 1 megawatt electrical reactor in a Titan base. To make that 1 megawatt of electricity, it might be throwing off 2 to 3 megawatts of heat. All that heat can be pumped into your habitats, your greenhouses, your ice melting systems. It keeps large volumes of air at room temperature, melts local ice into liquid water, and drives industrial processes like chemical reactors and metalworking. The surrounding ice and thick air act like a giant thermal buffer, smoothing out temperature swings. Your base becomes a warm island in a frozen world, held together by the same machines that give you electricity. So fission on Titan gives you both power and heat in exactly the place that needs them most. But there's another piece here. Titan is not just cold and dark, it is loaded with its own chemical energy in the form of hydrocarbons. So how do you plug that into the power picture? Titan's sky and surface are full of methane and ethane. It literally rains these hydrocarbons, and they collect in lakes and seas that hold thousands of cubic kilometers of the stuff, hundreds of thousands of cubic miles. Chemically, methane is simple. Take methane and burn it in oxygen, and you get carbon dioxide and water, releasing a lot of energy. The problem is, Titan's atmosphere has almost no free oxygen, but the surface is covered in water ice and water is just hydrogen and oxygen locked together. So your reactors do double duty. They provide the electricity to run electrolysis systems that split water ice into hydrogen and oxygen. You vent or store the hydrogen as needed and keep the oxygen. Then you combine that oxygen with Titan's methane. Now you have chemical fuel for aircraft, backup generators, peak power demands, even for rockets leaving the surface. In metric terms, methane stores about 55 megajoules of energy per kilogram. In more intuitive imperial terms, that's around 24,000 BTU per pound. A lot of punch for its weight. Titan hands you endless hydrocarbon feedstock. You just supply the oxygen and the ignition. So between nuclear reactors and methane fuel, Titan's power budget starts to look strong, not weak. But there's still more in the environment. Dense air and flowing liquids also mean other power options. So the next question is, can Titan's own weather and rivers help run your grid? Cassini's instruments measured winds on Titan. Near the ground, they're often calm or just a few meters per second, but remember, this is dense air. Even at modest wind speeds, a turbine can pull out good power because each cubic meter of air carries a lot of mass. A 10-meter diameter wind turbine, about 33 feet across, spinning in a 5 meter per second breeze, about 11 miles per hour, will deliver much more power on Titan than the same turbine in the same wind on Earth. Higher up, winds get stronger. That opens the door to tethered airborne turbines or kites that sit in the faster layers and send power down through cables. Then look at Titan's methane cycle. There are clouds, rain, rivers, and lakes. If you find regions where liquid methane flows down significant drops, tens to hundreds of meters, tens to hundreds of feet, you can in principle build hydroelectric systems. Picture liquid methane climbing up from rain and evaporation, then falling through turbines back into lakes. Titan's gravity is low, but the liquid is dense and the flows are long-lasting over Titan's long seasons, around 29 Earth years for a full Saturn orbit. None of these will replace nuclear as the backbone, but they can smooth demand, support remote outposts, and give redundancy if a main reactor goes offline. Together, nuclear, methane burning, wind, and maybe methane hydro form a layered energy system built entirely on local conditions, not on massive solar farms that barely work, Once you see that, a bigger pattern drops into place. Everywhere beyond Mars, sunlight is weak and unreliable. Europa, Enceladus, the dwarf planets, the Kuiper belt, all of them will need nuclear if we want to live there. So the real question is, where do you learn to run serious off-world nuclear industry without constantly risking Earth itself? Titan is the perfect lab for that. Its thick air and low radiation make the environment forgiving. If a reactor has a problem, the consequences are largely contained by the huge surrounding mass of ice and atmosphere. You have endless cold material to use as coolant and shielding. You can build, test, refuel, and even reprocess reactors using local water and hydrocarbons instead of shipping every gram from Earth. You practice closing fuel cycles, handling spent fuel, and running megawatt-scale plants for decades with minimal human intervention. By the time you can do that confidently on Titan, powering Mars becomes a much smaller problem. A nuclear plant in a milder, sunnier environment closer to Earth looks like an easy version of what you already mastered in deep cold. Solar on Mars becomes a nice supplement, not a fragile lifeline. Titan turns the scary part of deep space energy, nuclear at scale, into routine infrastructure. So if Titan is where we finally grow up about power, running whole cities on steady nuclear fire surrounded by stored chemical energy and dense air, the next issue is obvious. How much more does that environment give us in raw materials beyond just fuel? And what does that do to every factory, farm and lab we might want to build there? When you look up at Titan's orange sky, it just looks hazy and dead, so why do chemists see it as a planet-scale factory that's been running for billions of years non-stop? The gas up there is not simple. Titan's atmosphere is about 98% nitrogen, around 1.5% methane, and then a long list of trace chemicals, things like ethane, propane, hydrogen cyanide, and other nitriles and hydrocarbons. High-energy ultraviolet light from the sun and charged particles from Saturn's magnetic field keep slamming into those methane and nitrogen molecules. They break them apart, they shuffle the pieces, they build new, more complex organics called tholins. Those tholins are reddish-brown, sticky solids, and they likely fall out of the air and coat a lot of the surface like a very thin, fine dust or crust. In labs on Earth, when scientists try to copy Titan's atmosphere, they mix nitrogen and methane, chill it, hit it with ultraviolet light or electric sparks, and see what comes out. They consistently get organic gunk that includes building blocks of life, like amino acid precursors and other prebiotic molecules. On Earth, companies pay serious money to run that kind of complex chemistry in industrial reactors. On Titan, the atmosphere does it automatically over its entire surface, all the time. So when you breathe in Titan's story as a colony planner, what you're really looking at is a huge, slowly falling rain of useful chemistry. So you have a sky packed with nitrogen and active organics, and a surface dusted with tholin powder, and big pools of liquid hydrocarbons. The next question is, what can you actually build from all of that day to day inside a Titan base? Give a Titan settlement a couple of good reactors, some industrial scale heaters, pumps, and a few kilometers, a few miles of pipes and tanks, and you can feed entire chemical industries directly from the air and surface. You can separate out methane and ethane from the atmosphere and from the lakes. Methane becomes your primary fuel and rocket propellant. Ethane and heavier hydrocarbons become feedstock for plastics. With the right catalysts and reactors, you turn those gases into polyethylene and polypropylene, the same kinds of plastics we use for pipes, containers, structural panels, and even 3D printed parts. Need conduit for power lines, tanks, insulation panels, internal furniture, tools, drone shells, suit parts, all of that can be plastic. Titan lets you make it locally in bulk. On the fertilizer side, you combine nitrogen from the air with hydrogen from split water to make ammonia. From ammonia, you produce nitrates and urea for growing plants in greenhouses. Remember, on Mars you start with carbon dioxide and have to search hard for nitrogen just to get your first bag of fertilizer. On Titan, nitrogen is literally the main thing you're standing in at all times. The gas outside your habitat walls is your fertilizer factory just waiting to be tapped. That leads straight into the buzzword you hear all the time with Mars, in situ resource utilization, using local resources instead of shipping everything from Earth. On Mars, ISRU usually means taking carbon dioxide from the thin air, reacting it with imported or mined hydrogen, and making methane and oxygen. That's good, but it's only one main product chain. So how different is Titan's version of ISRU? On Titan, the use local stuff story runs on a totally different scale. You don't just have carbon in the air, you have fully formed methane everywhere, plus huge lakes and seas of it and related hydrocarbons. These bodies of liquid can be hundreds of meters deep, hundreds of feet, and stretch for hundreds of kilometers, hundreds of miles. Below that, the surface and shallow subsurface are likely layered with tholins and other organics, built up over eons. So instead of saying we'll make methane and oxygen here, you say methane is already here, in absurd amounts, and tholins give us raw material for more advanced chemistry. You're not setting up a small propellant plant next to a rocket pad. You're plugging into a multi-kilometer thick, multi-mile thick, organic system that the moon has been building for billions of years. ISRU stops being about one or two reactions and becomes about an entire local chemical ecosystem. Titan is preloaded, you just add machinery. Once you tap into that, you can close loops, and closing loops is what separates a temporary base from a real semi-independent civilization. So what does a closed industrial ecosystem actually look like on Titan in very simple steps? Start with water ice, which is basically Titan's bedrock. You mine ice blocks, melt them using waste to heat from your reactors, and feed the liquid water into electrolysis systems. Those systems split water into hydrogen and oxygen. You store the oxygen for breathing, industry, and combustion. You use some of the hydrogen to make ammonia with nitrogen from the air, which becomes fertilizer and industrial chemicals. Now bring in the methane and other hydrocarbons from lakes and the atmosphere. Burn methane with oxygen when you need high thrust power for rockets or peak electrical loads in generators, or run it through fuel cells for more controlled, efficient electricity. The exhaust is water and carbon dioxide. You condense the water and send it back to the electrolysis stack. You can feed some of the carbon dioxide into chemical reactors to build more complex organics, or simply vent it. Because Titan's atmosphere has so little CO2 that your emissions don't undo anything important locally. Meanwhile, nitrogen from the air gets fixed into fertilizers and nitriles, some of which become plastics, solvents, or specialty chemicals. Waste from one process becomes feedstock for another. Over time, the only major imports from Earth are high-tech items, things like advanced electronics, precision instruments and new reactor cores, bulk commodities, fuel, plastics, fertilizer, structural materials you make on Titan. That's what a self-sustaining colony really looks like. Not, we brought lots of stuff from Earth and hope it lasts, but the local environment and our machines feed each other. And that isn't just an engineering win, it hits humans on an emotional level too. So you have to ask, what does it feel like to live in a place that actually gives you resources by default, instead of a place that just strips them away? On a vacuum world or on Mars, the outside environment is basically an enemy. It tries to steal your air, your heat and your equipment. Every kilogram of material, every litre of water, every breath of oxygen is something you fought hard to keep or to mine from scarce deposits. That constant fight creates a culture of fear and scarcity. You're always a small accident away from serious trouble. On Titan, the outside is still deadly to an unprotected human, but the balance is different. The sky gives you nitrogen and organics. The surface gives you water ice and liquid hydrocarbons. Your reactors give you heat and power. Once you have the right systems in place, the environment starts to feel rich, not empty. Expansion is about adding new reactors, building more chemical plants, laying more pipelines, putting up more aircraft, not about battling just to scrape together enough basic air and water. People living there will notice that. They will know that the planet-scale chemistry around them is working in their favour. That mindset, this place gives us stuff, reduces the constant stress and opens more room for building, experimenting and taking smart risks. For a first major off-world civilization, that psychological shift matters. You want your settlers thinking about how to build bigger labs and better reactors, not panicking over whether they can squeeze enough oxygen out of rocks next month. So Titan's air and organics don't just keep you alive, they unlock full industry, closed loops, and a sense of abundance all in one package. But all of this chemistry is sitting on something, and that something is not dry rock, it's a deep shell of ice with a global ocean of water hidden below it. And that leads to the next critical question. If Titan already gives you a working atmosphere and a chemical factory on the surface, what happens when you start treating its ice and that buried ocean as your next layer of resources and discovery? People hear ice moon and think of a dirty snowball. So how big and serious does Titan look once you actually run the numbers on its ice and hidden ocean? Under the organics and hydrocarbons on Titan's surface, the solid ground is mostly water ice. Not a thin crust, but a shell probably tens of kilometers thick, maybe even more than 100 kilometers, so tens of miles of solid ice. Gravity data from Cassini, combined with how Titan flexes in Saturn's pull, point strongly to a global subsurface ocean under that shell. A layer of liquid water, probably mixed with ammonia and salts, sitting between two ice layers. Titan's radius is about 2,575 kilometers, roughly 1,600 miles, which means it's actually larger than the planet Mercury. This is not a small chunk of frozen junk. It's a full-scale world made of water and organics, with a deep internal ocean wrapped in thick air. For a colony, that means your ground is a structural material, a water mine and a shield, all at once. So the obvious next question is, what can you physically do with that ice right under your feet? On Titan, ice behaves like rock does on Earth. At Titan's surface temperature, around minus 179 degrees Celsius, minus 290 Fahrenheit, water ice is extremely hard and strong, stronger than many concretes here at home. You can cut blocks of it several meters thick, several yards, and they won't slump or melt. You can stack those blocks into walls, tunnels, and towers, then you take waste heat from your reactors and run it through pipes inside those structures. The inner surfaces warm slightly, just enough to soften the ice seams, then refreeze, that fuses blocks into a single solid dome or wall, almost like welding. A 3-meter thick ice dome, about 10 feet of ice overhead, gives you serious radiation shielding, structural strength, and a thermal buffer altogether. The outer part stays rock hard and extremely cold, blocking radiation and micrometeorites. The inner layers sit closer to 0 Celsius, around 32 Fahrenheit, which makes them easier to work with. You can even slowly melt a small thickness from the inside for fresh water, while leaving most of the dome intact. On Earth, mass is your enemy for space construction, because lifting heavy material off the surface costs huge energy. On Titan, mass is everywhere and gravity is weak, so you get all that shielding and structure almost for free. That feeds straight into the next point. Water is life support, industry, and agriculture. So how different is water access on Titan compared to Mars, where we've already pinned so many hopes? Mars does have water. It's locked in the polar ice caps and in buried deposits closer to the equator. But getting to it often means digging through dry dust and rock, then hauling that icy soil back to a processing plant, then heating it with precious energy to release liquid water. The layers can be patchy, so you have to search for good spots, and moving heavy loads in 0.38 G still takes serious machinery. On Titan, the rock itself is almost pure water ice. If you dig down 1 meter, about 3 feet into the surface, nearly everything you pull up is water in solid form, with some organics mixed in. Every cubic meter of that ice weighs around 900 kilograms, about 56 pounds per cubic foot. Drill a vertical shaft 10 meters deep and 10 meters across, roughly 33 feet by 33 feet, and you've freed on the order of hundreds of thousands of kilograms of ice. That's enough water to support a small colony's drinking needs, greenhouse irrigation, and many industrial uses for years once melted and cleaned. And you did it in a single small excavation. Because ice is everywhere and easy to reach, you can place bases where it's best for sunlight, communications, or access just to lakes, without worrying about is there water here. The answer is yes, under every step. That's a totally different starting point from Mars, where follow the water narrows your choices. But the real wildcard isn't the solid ice, it's the liquid water ocean below it. A global ocean in the dark, under pressure, running for who knows how deep. So what does that imply for science and for the long-term goals of a Titan civilization? If Titan's subsurface ocean is tens to hundreds of kilometers deep, tens to hundreds of miles, it's a massive volume of water. Tidal forces from Saturn flex Titan's interior, which can create heat and drive circulation in that ocean. Salts, ammonia, and other chemicals can dissolve in it. That means you likely have layers with different temperatures and compositions, chemical gradients and energy flows. On Earth, those ingredients, in our oceans and deep hydrothermal systems, are strongly tied to life. No one is saying Titan definitely has life in its buried ocean, but if it does, it will almost certainly not look like anything we know. Even if it doesn't, the chemistry there could be a different route toward complex molecules. The problem is access. Drilling through tens of kilometers of ice is far beyond our current tech. You need serious industry to even think about it. Heavy drills, heat sources, power, long-lived robots. A base on Titan is what gives you that industrial muscle. You won't be melting through the shell with a single lander. You'll be doing it with machines built and serviced by a growing settlement that has power, materials, and people on site. On Mars, the big astrobiology target is ancient riverbeds and lake beds, dried up sediments that might hold chemical traces, or fossils of microbes that died billions of years ago. That's important, but it's mainly about the past. On Titan, the target is a whole second ocean system that's currently active, right now, sitting under your boots. You're not only reading history, you're probing a live experiment. If we eventually reach that ocean and drop instruments inside, we'll get data on how water behaves, how chemistry organizes itself, and maybe how life could arise under conditions totally different from Earth's surface. That alone justifies a Titan base scientifically. But step back and look at the bigger pattern. In one solar system, you now have Earth with a global ocean and Titan with a global ocean. One is warm, sunlit and oxygen-rich. The other is dark, cold and maybe mixed with ammonia and other antifreezes. That two-ocean situation is not just cool trivia, it's a massive opportunity. It means we can test ideas about how common life is and how flexible it can be using two completely different water worlds under one star. If you care about understanding not just life as we know it, but life as it could be, going to the dry Martian desert first is the conservative limited choice. Going to Titan first is the bold one. You are moving into a place where the surface has one kind of liquid, methane and ethane, and the interior has another, water. Two stacked oceans, one of hydrocarbons, one of water, both possibly active. Living on Titan puts your colony right on top of that double system. Your industry pulls ice from the shell. Your chemistry uses hydrocarbons from the surface seas. Your science plans long missions aimed at the buried ocean. You're literally sitting between two worlds in one body, a chemical ocean above and a water ocean below. So if Titan offers a working atmosphere, endless ice, and a hidden ocean that might host totally new chemistry or even strange life, the next step in the argument is obvious. Which world is actually better for answering the deepest question of all? How does life begin, and are we alone? The dry, irradiated surface of Mars, or a frozen time capsule of early Earth-like chemistry running in slow motion on Titan? If you had a chance to see early Earth before life really took off, would you pick the dry Mars desert, or the one place that actually copies our planet's first atmosphere in slow motion? Geology and atmosphere models say early Earth probably had a thick blanket of nitrogen, a lot of methane, and a constant haze of organic particles in the sky. That's not science fiction, that's serious research. Now look at Titan today. Surface pressure around 1.5 bars, thicker than Earth's. Atmosphere mostly nitrogen with methane mixed in. A global orange haze that blocks much of the sunlight and lets only a dim glow hit the ground. The surface is way too cold for liquid water, but the chemistry in the air, the way methane and nitrogen get broken apart and rebuilt. looks a lot like what we think was happening in Earth's upper atmosphere billions of years ago, just slowed down by the cold. Huygens and Cassini both measured complex organics forming in the air and falling out constantly. So when you stand on Titan, you're basically standing inside a full-scale frozen copy of young Earth's chemical lab. So if Titan is already acting like a time machine to early Earth, what happens when you stop just watching it and start running actual origin of life experiments right there? On Earth, scientists have already tried to fake Titan's chemistry. In labs, they take nitrogen and methane, chill them, blast them with ultraviolet light or electric sparks and see what they get. The result is Tholin gunk. But that gunk isn't random. It contains amino acid precursors, pieces related to nucleobases, and a whole spread of complex organic molecules that look like the sort of stuff you might want around if you're trying to build life from scratch. These are the kind of experiments that made early Earth research famous, but here they're tuned to Titan conditions. Now scale that up from a glass chamber on a lab bench to a whole world. If you have a base on Titan, you're not limited to tiny samples. You can pull air from different heights, scoop surface material, drill shallow cores, sample lakes, and do it repeatedly, across different seasons, over distances of thousands of kilometers, thousands of miles. You can set up instruments that just sit and watch how the chemistry changes over years. You're not guessing what might happen in a methane-nitrogen atmosphere. You're measuring what is actually happening in real time on a planetary scale. But chemistry on Titan is not just an early Earth replay. It also runs in a solvent we've never seen life use before. So the next question is, how does biology change when the liquid you work with isn't water at all? On Earth, life uses liquid water for everything. Cells are basically water bags filled with dissolved molecules. Reactions run fast because the temperature is relatively warm and water is a very flexible solvent. On Titan's surface, the liquids are different. The lakes and seas are mostly methane and ethane, and the temperature is about 94 Kelvin, around minus 179 degrees Celsius, minus 290 Fahrenheit. At those temperatures, chemistry crawls, but it does not completely stop. Some researchers have suggested that under those conditions you could get cell-like structures made out of materials like acrylonitrile, forming flexible membranes that work in liquid methane. They have even given these hypothetical structures a name, azotosomes. We don't know yet if anything like that exists on Titan, but the key point is this: you suddenly have to think about life, or at least life-like chemistry, in a solvent that is not water, at a temperature where our normal rules about reaction speed and stability start to bend. A base on Titan lets you dive into that second solvent world. You can send floating probes into methane lakes, drop chemical sensors into streams, and run long-term tests on how complex structures behave in those fluids. You're not just checking, is there Earth-like life here? You're pushing the boundary of what lifelike can even mean in the first place. Now compare that to Mars. What exactly are you asking Mars to answer, versus what you're asking Titan to answer? Mars is about history. Was there ever liquid water on the surface for long periods? Yes. Did that water create conditions where simple life could have formed? Maybe. If it did that life leave any fossils or chemical traces in ancient sediments or subsurface ice? That's the main focus. You dig in old lake beds, drill rock cores, and look for signs that something once lived there and died long ago. That's valuable, but it's mostly a backward-looking question. Did it ever happen here? Titan is more sideways. It doesn't look like Earth. It doesn't have surface oceans of water. It's cold and dark. But it might be running right now a full planetary experiment in complex organic chemistry in conditions that do not match Earth's at all. The question on Titan isn't just, was there life? It's, can life-like chemistry organize itself in a world this different today? If the answer is yes, if you find something that really counts as life in methane lakes or in the subsurface ocean, then you've basically proved that life is not rare at all, because it has appeared twice independently in one solar system. If the answer is no, if the chemistry gets close but never really organizes, you still win, because you learn hard limits on what conditions can and can't make life. But you cannot get those answers with one probe and a quick flyby. you need time. So the key question becomes, what does a permanent base add that a few landers and orbiters never can? A single robot gives you a snapshot. A handful of missions over a decade gives you a short movie with missing frames. A base gives you a continuous record. You can keep instruments running through multiple Titan seasons, each season being years long. You can track how haze production shifts as sunlight angles change, how lake levels rise and fall, how surface chemistry evolves, how trace gases in the atmosphere creep up or down. You can take long-term samples from the same site year after year to see if anything is slowly changing or organizing. Inside the base, you set up dedicated Origin of Life labs, fed by fresh Titan material. You can run experiments that last for years, not just weeks, leaving reactors to sit at Titan temperatures, with Titan pressures and Titan mixtures, and check them periodically. You can adjust conditions, tweak energy inputs, and watch how far the molecules go on their own. This is the kind of deep, slow science we only really learned to do for Earth's climate and ecosystems once we built permanent observatories and long-running stations. Titan with a base becomes that kind of observatory for prebiotic and maybe even exotic biotic chemistry. Meanwhile, Mars, if we rush to colonize it first, turns from a clean natural record into a contaminated mix of Earth microbes and Martian rock. The window to get pure data closes fast. So if your real goal is to answer the biggest question humans have, how did life begin, and how many ways can it begin? The obvious move is not to plant your first big city on a dusty, irradiated surface and hope we don't ruin the forensics. The obvious move is to plant that city on a world that is already running the right chemistry, where you can watch the process without frying people, and where time is on your side. But to do that, you have to accept one more hard truth. Titan will never be warm. Its surface will always sit near minus 179 degrees Celsius. Its air will always be thick and cryogenic. To turn Titan into our first big lab city, we have to prove we can engineer everything, from suits to machines to whole power plants, to run smoothly at those temperatures for decades. So the next question is blunt. If we pick Titan first and commit to that deep cold, can we build technology that doesn't just survive at minus 179, but actually treats that extreme cold as an advantage instead of a weakness? Most people hear minus 179 degrees Celsius and just think, very cold. But do you actually understand how brutally different Titan's cold is from anything your normal hardware can handle? Most everyday plastics and rubbers start to go stiff and crack well before minus 50 Celsius, about minus 58 Fahrenheit. Greases thicken, seals leak, hoses snap if you bend them. Titan doesn't just nudge past that, it obliterates it. At around minus 179 degrees Celsius, minus 290 degrees Fahrenheit, structural metals shrink, different parts contract by different amounts, bolts loosen or over-tighten, lubricants freeze solid, and many common fluids just stop flowing. Electronics behave differently too. Batteries lose most of their capacity, some semiconductors drift out of their normal ranges, solder joints get stressed by thermal cycling. The key point is, we already know how to make small machines survive those conditions. Cassini's domain instruments, the Huygens lander, and other outer planet probes ran at these temperatures. We've used special alloys, heaters, and insulation to keep them working, but that was for a few spacecraft. Titan forces you to scale that knowledge up from a box of instruments to an entire city, every valve, every door, every robot, every cable. You don't get to cheat with shirt-sleeve temperatures outside like on Mars at midday. You commit to building a culture of cryogenic engineering from the start. The flip side is, in that environment, heat becomes the most precious resource you have, not something you're desperate to dump into space. So how does that change the whole logic of your power and infrastructure? On Earth and Mars, big reactors and factories have a waste heat problem. Every megawatt of electricity they generate comes with 2 or 3 megawatts of heat you need to get rid of using cooling towers, radiators, fans. On Titan, you flip the sign. Every watt of electric power is accompanied by 2 or 3 watts of free heating you absolutely want. A 1 megawatt electrical reactor running for a year throws off something like 31,500 gigajoules of heat. In imperial terms, you're talking on the order of tens of trillions of BTU. On Titan, almost all of that can be used. You pipe that heat through your habitats to keep air at room temperature. You feed it into heat exchangers that melt ice into water. You store it in big thermal masses, tanks of water, blocks of rock, even large volumes of ice that you slowly warm. Those act like batteries, smoothing out demand. Your base becomes a controlled warm bubble carved into frozen ground, stitched together by a network of hot fluid loops instead of just electric wires. Waste heat is the glue that holds the whole system above freezing. Outside, that same mindset continues. Suits, vehicles, machines, everything has to be built not to hold air against vacuum, but to hold heat against a dense, cryogenic atmosphere. So what does that actually do to the way you design gear for people working on the surface? A Titan EVA suit does not need to fight a near vacuum like on Mars or the Moon. You're stepping into an atmosphere at about 1.5 bar. You still need your own oxygen and you need to keep the methane and nitrogen out of your lungs, but you don't have to maintain a huge pressure difference across the suit wall. So instead of a rigid, balloon-like shell, you build a heavily insulated, flexible suit. More like extreme polar gear combined with a scuba system. The main job is to keep body heat in and cold out, not to stop the suit from inflating and exploding. Vehicles follow the same logic. You can get away with cabins that are only slightly pressurized compared to outside, or even unpressurized cockpits if operators wear suits. What you absolutely must have is heating, insulation, and components that don't seize up at Titan temperatures. Lubrication moves from liquid oils to solid-state bearings, special cryogenic greases, or magnetic and ceramic designs that barely need lubrication. By solving those problems on Titan, you automatically solve them for other deep cold environments. Europa's surface, Enceladus, Kuiper belt objects, even long-duration hardware in the outer asteroid belt. One design effort buys you a toolkit for most of the solar system's real estate. And that's not just about comfort, it's about robots. Most of the mass you move and work you do in the outer system will be done by machines, not people. So Titan becomes the place where we find out which materials, which joint designs, which electronics actually last decades in deep cold. That's something Mars will never force you to learn. So ask yourself, do you want your first big engineering school for deep space to be locked into warm rock conditions? Or do you want it stress-tested where almost everything else in the solar system already sits? Most of the solar system, by area and by mass, is cold and far from the sun. Asteroids that never come close in, dwarf planets in the Kuiper belt, outer moons of Jupiter and Saturn, all of them live at temperatures similar to or below Titan's. Starting with Mars trains you to build gear for a narrow band of conditions: thin air, moderate cold, lots of dust. Useful but very local. Starting with Titan trains you to build hardware that works almost anywhere solid and cold. You develop libraries of alloys that don't crack, seals that don't leak, cables that stay flexible, and robots that don't die after a few thermal cycles. That's like building a master Lego set for exploration beyond Jupiter. Every mission to an icy moon, every mining platform on a cold asteroid, every station in the distant Kuiper belt pulls pieces from the Titan-tested kit. You spend the hard research time once at Titan instead of reinventing solutions for each new target. And here's the punchline on the engineering side. Once you can run fission reactors, life support, construction equipment, aircraft, and full industrial chains in an atmosphere at 1.5 bars at minus 179 degrees Celsius, with barely any sunlight, working in a place like Mars with warmer temperatures, more solar energy, and shorter communication delays starts to feel like easy mode. On Titan, you design for maximum insulation, for crazy cold, for slow chemistries and heavy air. Move those same designs inward and suddenly your radiators work better. Your solar panels finally matter, your suits have extra safety margin, and your machines feel over-designed in a good way. The arrow only goes one way. If you can make a system that thrives on Titan, you can adapt it to Mars, to the Moon, to asteroids without much trouble. But if you only ever design for Mars, your tech will crack and stall the first time you try to push it into true deep space. So by choosing Titan first, you're not just picking a place to live, you're picking the hardest practical environment where humans can still operate on the surface and building your entire technology base around surviving that. Then, later, everything closer to the sun is a step down in difficulty. But there's another dimension we haven't touched yet, one that isn't about hardware at all. While you're turning Titan into an engineering testbed and a city, Mars is sitting there with a fragile record of possible ancient life in its rocks and ice. And once we turn Mars into a construction site, that record starts to blur. So the next serious question is, if we rush humans to Mars first and start digging, drilling and leaking microbes everywhere, what exactly are we erasing? And is Titan our last real chance to practice off-world living without destroying the best crime scene for ancient life we've ever had? When you talk about sending people to Mars, you're not just planning a mission, you're walking into a crime scene, so how careful do you actually want to be before you start stomping all over the evidence? If Mars ever had life, even simple microbes, the best record of that is locked in old sediments, buried ice, and maybe in salty underground pockets. That's where chemical traces, microfossils, or even dormant cells could still be hiding. Every lander we've ever sent carries stubborn Earth microbes even after strict cleaning. They ride in tiny cracks, in shadows, in films on metal. A few probes is one thing, but once you start building permanent bases on Mars, you're talking about people exhaling trillions of bacteria, leaking tiny amounts of waste, driving vehicles that grind dust into the air and across the ground, drilling deep holes and leaving gear everywhere. That kind of contamination is one way. You can't hit reset once it happens. Later, when you drill a core and find microbes, you might never be sure if they're Martian or just a distant cousin of something that came off a human glove 40 years earlier. If you care about answering, did Mars ever host life? In a clean, unambiguous way, the only honest move is to keep large human presence off Mars until we've done the careful robotic detective work first. That means ultra-clean drills into subsurface ice, properly isolated sample returns, and broad mapping of the most promising sites before we turn the place into a construction zone. Titan, by contrast, is dangerous in a different way, but it's far less matched to Earth biology, and that matters for contamination risk. So what does that actually buy you? Titan might have its own form of life, but if it does, it's almost certainly not like us at the surface. Earth microbes need liquid water, moderate temperatures, and in many cases oxygen or similar chemistry. Titan's surface offers liquid methane and ethane at about 94 Kelvin, minus 179 Celsius, minus 290 Fahrenheit. That's so cold that water is rock and Earth microbes are basically frozen solid. They can hitchhike on hardware, but they're not going to be happily swimming around in methane lakes, metabolizing and reproducing. That doesn't mean there's zero risk. You still have to be careful, but the odds that Earth organisms quickly invade and mask native surface biosignatures are low. The subsurface ocean is a different story. Down there you probably have liquid water, maybe with ammonia and salts, warmed by internal heat. That kind of environment is closer to something microbes might manage in. So a Titan base still needs serious planetary protection rules before it starts drilling all the way through the ice shell. But while you're just living on the surface, exploring the air lakes and upper crust, your biological footprint is much easier to track and separate from any native signals. That leads to a bigger framing. Do you want humanity to be the main contaminant in its own experiments, or the main instrument? If we go Mars first with big bases, we effectively turn ourselves into the worst contaminant we've ever introduced into a lab. Our own biology floods the environment we're trying to study. We will spend the next century arguing over whether any signals we see are truly Martian or just us echoing back. If we go Titan first, we put our first dirty off-world civilization in a setting where Earth-like life is already on the back foot, and where the big questions are mostly about non-Earth-like chemistry anyway. We still have to be careful, but the baseline environment is less compatible with our microbes, so our noise level is lower. At the same time, a Titan base forces us to master closed-loop ecosystems and strict internal biosafety. You'll recycle almost everything inside the habitat because importing bulk supplies is costly. You'll track microbes, manage waste, and monitor air and water quality in a fully sealed system surrounded by lethal cold. Those are exactly the skills you want learned and debugged before you put a million-person city on Mars. By then, you'll know how to keep your biology where it belongs and how to keep it out of science targets. There's also a moral side here that people like to slide past. If Mars once had its own biosphere, and if the clearest remaining record of that is in its untouched rocks and ice, then erasing or obscuring that with our first wave of settlements is not just bad science, it's throwing away a unique chapter of the universe's history. You don't get a second Mars. If we contaminate it so thoroughly that we can't tell what was original and what was imported, that loss is permanent. By choosing Titan first, we buy time. Time to send more precise orbiters and landers to Mars. Time to drill cleaner, deeper cores in multiple locations. Time to run at least one solid sample return program, where rocks and ice come back to Earth labs under controlled conditions, before we start mixing human biology into the equation. Titan lets us practice long-term off-world living, with all the hard parts of power, structure, and life support, without parking our first city on top of the clearest fossil record we're likely to find in the solar system. This is the compromise nobody really sells in the popular story. You don't have to choose between going big and going careful. You can push outward hard on Titan, build real cities, test reactors, grow food, raise families, learn all the engineering lessons of being a multi-world species, while keeping Mars as a protected archaeological site for a few more decades. We explore and expand on Titan. We probe and preserve on Mars until we know what's there. Then, once we have that Mars story as clean as we can reasonably get it, we make a conscious decision about how to colonize it, fully aware of what we're trading away. At that point, we'll be coming from a civilization that already understands closed ecologies and planetary protection into practice, not just on paper. So if Titan lets us grow up as a spacefaring species without wiping our best evidence off the map, the next strategic question is this. When that Titan civilization starts building ships and fuel depots, where in the solar system does it actually send them first? And does Titan quietly become the main launch pad for everything that happens beyond the asteroid belt? We've talked about Titan as a place to live, but here's the bigger question. Once you're settled there, does it also become the main launch pad for everything we ever do in the outer solar system? Look at the basic layout. Titan orbits Saturn roughly every 16 Earth days at about 1.2 million kilometers from the planet, around 750,000 miles. On the surface, gravity is only about 0.14 g, and the escape speed is around 2.6 kilometers per second, about 1.6 miles per second. Compare that to Earth's 11.2 kilometers per second and Mars's 5 kilometers per second. A rocket leaving Titan for low orbit needs far less velocity than the same rocket on Earth or Mars. In rocket terms, lower required speed means less propellant, smaller tanks, and far more room for cargo. Now combine that with Titan's energy resources. You have methane everywhere, in the air and in deep lakes. And you can make oxygen by splitting local water ice with power from your reactors. That means Titan can run propellant factories directly on the surface. You produce methane and oxygen, pump them into tanks, and launch them to orbit using relatively small reusable vehicles. Each flight doesn't need to be a giant one-shot stack like a Saturn V. It can be more like a robust industrial truck making regular rounds, filling depots in Titan orbit with fuel. Once you have fuel depots and some dry docks in orbit, Titan starts looking less like an outpost and more like a service station and workshop for the whole outer system. So how does that actually change getting to the really distant worlds like Uranus, Neptune and the Kuiper belt? From Titan orbit, your ships sit deep in Saturn's gravity field. That sounds like a problem, but you can use it. By timing burns and flybys properly, spacecraft can steal a bit of energy from Saturn's motion, the same way probes steal energy from Jupiter today. If you launch from Earth, your rocket has to haul all its fuel up from a deep gravity well and then push against the sun's pull almost entirely on its own. If you assemble and fuel your ship in Titan orbit, you've already saved a big chunk of that work. In pure speed terms, shaving just 1 or 2 kilometers per second off the total delta V budget The total speed change you need over the whole mission may not sound huge, but in rocket design it's a game changer. It can mean the difference between a vehicle that is mostly fuel mass and one that is mostly payload. In more everyday terms, it's like the difference between a truck carrying mostly gas with a tiny cargo area and one carrying a full load of goods with only a modest fuel tank. That advantage compounds as missions get more ambitious. If you're going to Uranus, Neptune, or way out into the Kuiper Belt, every kilometre per second you don't have to supply from your own tanks frees up massive mass and cost. Titan, with its easy launches and built-in fuel production, becomes the place where you top up before making those deep runs. Take it one step further. At some point, we'll want to send probes far beyond the planets, thousands of times the Earth-Sun distance away, maybe even on paths that approach other stars. Where do you want to build and fire up those first real interstellar-class machines? Doing that from Earth orbit ties you to tight safety and constraints around nuclear propulsion. Nuclear electric or nuclear thermal engines are efficient for deep space travel, but nobody is excited about lighting off giant nuclear stages right next to the planet. Titan gives you an alternative. You build the big stages in Titan orbit, using structures and some components made on Titan, then fuel them with methane, hydrogen or other propellants produced locally, and only then do you turn on the nuclear drive far from Earth. Those tugs can slowly but steadily push interstellar probes up to 20, 30, 50 kilometers per second, about 45,000 to 110,000 miles per hour, without dumping any of that propulsion risk into Earth's environment. Titan becomes the quiet Saturnian shipyard where we learn how to assemble and operate starbound hardware at scale, with thick shielding, lots of coolant, and plenty of cheap fuel a short flight away. When you chart out that kind of network, you start to see a key pattern. Mars is not a hub. It's a side branch, while Titan can be a backbone. So what does that do to the Mars First roadmap that everyone repeats? A Mars First plan builds one big branch off Earth. You go Earth, Moon, Mars, maybe some asteroids, and you pour most of your resources into that one direction. It's valuable, but it's narrow. A Titan First plan builds a central node. From Titan, you can go inward to Mars and the asteroid belt with refueled ships and proven nuclear power, and outward to Jupiter, Saturn's other moons, Uranus, Neptune, and beyond. Instead of a single path, you get a web. Titan is set up almost perfectly for that role. It has atmosphere for aerobraking and parachute landings, so heavy cargo can arrive more safely. It has low gravity for cheap launches. It has enormous quantities of chemical energy in its hydrocarbons. It has water ice for oxygen and hydrogen, and it pushes you into nuclear power, which you need for everywhere else beyond Mars anyway. In a long-term view where the whole solar system is potential living and working space, hubs like that are what actually matter. And here's the twist a lot of people miss. Even if you emotionally want Mars more than anything, by the time you're technically ready to build serious cities there, you're also, almost by definition, capable of reaching Titan. Serious Mars bases need reliable nuclear power, not just solar panels, especially through dust storms and winters. They need cryogenic propellant handling for methane and oxygen. They need hardened autonomous robots that can work for long stretches without constant human supervision. Those are the same core technologies you need to send big, durable missions to Saturn. So by the time you can say, we're ready for a real large-scale Mars colony, you've built almost all the tech you need for Titan as well. Stopping at Mars at that point is like doing most of a long hike and turning back just before the viewpoint. If instead, you tie Mars into a Titan-anchored network, Mars stops being the end goal and becomes one connected world among many. You launch hardware from Earth to Titan, build and fuel deep space ships there, then send some inward to Mars, some to the asteroids, some outward to the gas giants. All the projects reinforce each other. So by putting Titan first in the big roadmap, you're not ignoring Mars. You're setting up the infrastructure that makes Mars and everything else easier and cheaper to reach. But this isn't just about rockets and fuel and launch speeds. Titan also gives you something else that's easy to underestimate. Completely different climate and atmospheric system to study in parallel with Earth and Mars, which feeds straight into how we understand planets and even exoplanets at a deep level. So the next question is this. If Titan's atmosphere and methane weather cycle are so extreme compared to ours, how much do we actually gain for Earth and for future terraforming by living inside that alien climate and watching it work from the ground up? We talk about Titan as a place to live and launch from, but there's another angle that's just as important. How much does living inside that weird atmosphere upgrade our whole understanding of planets, including Earth? Titan's surface sits at about 94 Kelvin, roughly minus 179 Celsius, minus 290 Fahrenheit. That's not only because it's far from the sun, the way its atmosphere handles energy is wild. You've got a thick nitrogen blanket, methane mixed in, and a global haze of hydrocarbon particles. That haze blocks and scatters a lot of incoming sunlight before it reaches the ground. At the same time, greenhouse gases in the lower atmosphere trap infrared radiation coming up from the surface. So sunlight in is reduced, heat out is also reduced. The net effect is what scientists call an anti-greenhouse layered on top of a greenhouse. It's a delicate energy balance that locks Titan into a very stable deep freeze. If you can build climate models that match Titan's temperature profile, haze structure, and methane cycle, you've proved those models can handle conditions totally outside Earth's usual range. You're stress testing your physics in a regime where your intuition is mostly wrong. That's exactly what you want if you plan to trust those models when they tell you what Earth or Mars will do under extreme changes. But Titan isn't just a cold ball with fancy radiative physics. It has weather, real weather. So what does a full active methane cycle give you that Mars just can't? On Earth, water runs the show. It evaporates from oceans and lakes, condenses into clouds, rains, flows in rivers, and sinks into the ground. Titan does the same thing, just with different liquids. Methane and ethane evaporate from lakes and moist ground, form clouds, and then fall as rain, mainly around the poles. Cassini saw cloud systems and storms. Radar mapping showed lakes and seas that can be hundreds of meters deep, hundreds of feet, connected by river channels and valleys carved into the icy crust. So you've got evaporation, condensation, rain, runoff, infiltration, all the same steps as Earth's hydrological cycle, but in methane at 94 Kelvin. If you put a base there and scatter weather stations, radars, and lake probes around the region, you can watch that whole cycle in detail over years. You can see how often it rains, how fast lakes refill, how storms build and die. That lets you test which parts of our climate theory are truly general and which parts are just accidents of living on a warm, water-based planet. Once you can write models that handle both Earth's water cycle and Titan's methane cycle correctly, your tools suddenly get much more powerful. So how does that feed back into things we care about closer to home? If a model can reproduce Earth's climate and Titan's climate using the same core physics, then you've shown it works over a temperature range from 94 Kelvin up to around 288 Kelvin, from about minus 179 Celsius to plus 15 Celsius, or minus 290 to about 59 Fahrenheit. You've also shown it works across atmospheres that are light on carbon dioxide and heavy on nitrogen, and with different kinds of hazes and clouds. That means when you ask that model, whoa, what happens to Earth if we change greenhouse gases this much? Or what happens if we try to warm Mars this way? You're trusting code that's already survived extreme tests. Titan's thick air and slow winds also give you a natural planetary scale wind tunnel. You can study how turbulence develops in dense atmospheres, how storms evolve under dim light, how haze layers interact with cloud decks, all in a way that complements what we see on Earth and Mars. That boosts not just climate science, but aircraft design and entry descent landing tech for future missions. There's another puzzle baked into the Titan that goes straight at long-term planetary evolution, and that's its methane. Methane in an atmosphere doesn't last forever under sunlight. It gets broken down over tens of millions of years, yet Titan still has a lot of it. So what is keeping that methane topped up? If Titan's methane has been hanging around for billions of years, something has to be replenishing it. Possibilities include cryovolcanism, where icy volcanoes or warm spots leak methane from the interior, or the breakdown of methane-rich clathrates, ice structures that trap gas and later release it. There are even more exotic ideas, but the point is the same. There is an active source somewhere. A base can go after that directly. You can set up seismometers to listen for internal movements, heat flow probes to map warm regions, gas analyzers to track tiny changes in methane and other species over time, and orbital and surface instruments to look for signs of active vents. In effect, Titan becomes a giant clock cycling methane over millions of years. Cracking that clock tells you how volatiles move inside cold, rocky, icy worlds, which feeds back into how we think Mars lost its atmosphere, how early Earth handled its gases, and how exoplanets might evolve. Put all of this together and you get to the core data argument. Right now we have one excellent climate record, Earth's. We have a growing but still limited one for Mars, mostly from orbit with a few surface points. Titan's record is the one that will really push our understanding to the edge. If we put a permanent base there, with weather networks, deep time chemistry experiments and constant monitoring, we're not just buying security for the people who live under that orange skewer, we're buying the data set that will train and test every advanced climate model we ever write for this solar system and for exoplanets around other stars. That means Titan is not a side project in the story of planetary atmospheres. It's the lab where we learn which of our ideas survive contact with a world that breaks all our casual assumptions. From there, when we look at a hazy exoplanet spectrum or think about terraforming Mars, we're not guessing, we're applying lessons from a world we've actually lived on. But none of this data, none of this physics, changes the brute reality underneath every long-term space project: cost, logistics, and risk. So the question you have to confront next is simple and sharp when you factor in travel times, launch windows, mass budgets. And what you actually get back for the money. Does Mars really beat Titan? Or does the numbers game, just like the physics, quietly tip in Titan's favour too? Mars is closer and faster to reach. That part is obvious, so why doesn't that automatically make it the smarter long-term bet? Look at the raw travel times. A standard Hohmann transfer to Mars takes about 6 to 9 months each way, and you only get a good launch window roughly every 26 months. Titan, even with smart gravity assists and chemical rockets, is a 6 to 8 year trip with today's style of mission planning. That sounds brutal if you're thinking about sending people. But for heavy cargo like reactors, factory modules and bulk supplies, time is not the main cost. Mass is. Rocket launches are priced in kilograms and tons, not in calendar pages. If you launch, say, 100 tons, around 110 tons of nuclear reactors, chemical plants and life support hardware to Titan, and that equipment runs for 30 or to 50 years with minimal resupply, you've got an asset that pays off for decades. If you instead rush to Mars with lighter, underpowered setups because you want them there in 6 months, and then you have to keep sending regular shipments just to keep the base functioning, you've traded distance for permanent dependency. The short trip feels good, but the bill never stops. Titan asks for patience up front and gives you a much more stable, heavy infrastructure once you're there. Even if you accept the longer travel time, there's another penalty: the speed of light limit on your command and control. So how much does Titan's huge communication delay really hurt? And what does it force you to build? Mars sits between about 4 and 24 light minutes away one way, depending on the orbits. That already makes real-time control impossible, but you can still do short back-and-forth exchanges in under an hour. Titan is worse. Light takes more like 60 to 90 minutes one way. That's a minimum 2 to 3 hours for a round-trip signal, often more. You're not flying a Titan drone like a remote control toy from Earth. By the time your command arrives, the local situation has changed. At first glance, that seems like a major downside. In reality, it just shoves you where you're going anyway, into full autonomy. Machines and software on Titan have to make decisions locally. Rovers and aircraft need onboard navigation and hazard avoidance. Reactors need smart control systems that don't wait for every instruction. Life support systems need automatic fault detection and correction. That same autonomy, once developed, comes back home. It makes Mars missions smoother because now your robots there are smarter. It makes asteroid mining less labour-intensive. It improves terrestrial robotics from remote mining to disaster response. Titan forces your tech stack into the deep space regime instead of letting you sit in a comfortable half-manual control zone. So if time and delay can be handled with smart design, the next logical question is, what do you actually get out of Titan economically that you can't just get easier from Mars or from asteroids? Mars supporters often talk about mining, metals, water, maybe fuel production. But if you look closely, almost all of those raw materials are also available in asteroids and smaller bodies, which are easier to escape from because of their tiny gravity. You don't need a planet-sized gravity well to give you iron, nickel, water ice, or carbon. Asteroids and small moons can supply that with less delta-V penalty. Titan's value sits on a different axis. First, knowledge. It's a live lab for origin of life chemistry, for exotic surface liquids, for subsurface oceans, for anti-greenhouse atmospheres. Discovering or ruling out methane-based life, understanding how tholins behave over geologic time, pinning down the source of Titan's methane, those are all fundamental science wins. Second, technology. To live there, you must develop compact, safe nuclear power, ultra-reliable cryogenic systems, advanced autonomy, and closed-loop life support. Those technologies will be in demand everywhere else in the solar system and on Earth. Third, chemical feedstock. Titan gives you thick nitrogen and massive hydrocarbons for making plastics, fuels, solvents, fertilizers, and more. On a per kilogram basis, the intellectual property and design know-how you get from mastering Titan is worth far more than any ore you could ever ship back. That IP over ore focus also shows up in how Titan development feeds improvements at home. So what kind of spin-offs do you get on Earth by committing to a Titan-level engineering challenge? To build a Titan base, you need nuclear reactors that are incredibly reliable, efficient, and safe in harsh conditions. Those design lessons fold straight into next-generation reactors on Earth, from remote communities to grid-scale plants. You need cryogenic storage that can hold liquids for years with minimal loss, which improves everything from liquefied natural gas transport to superconducting magnets. You need insulation that can handle extreme temperature differences, which helps buildings, vehicles, and refrigeration on Earth cut energy use. Robots built for Titan will have to work day in, day out at minus 179 degrees Celsius in dense, cold air. If you can get a maintenance robot to function routinely in that environment, operating the same design in an Arctic winter at minus 40 Celsius, minus 40 Fahrenheit, suddenly looks simple. You've just built an entire line of hardware that can work in polar research, high-altitude aviation, deep mines and disaster zones without failing the moment things get rough. All of that is upside, but you can't ignore risk. What happens if we bet everything on Mars, and Mars turns out to be a much worse home than we hoped? There are open questions about Martian dust toxicity, long-term low-G health effects, radiation, and geology. Maybe the dust turns out to be much more harmful to lungs and equipment than we think. Maybe shielded habitats still leave people with too much radiation over decades. Maybe the regolith chemistry makes agriculture harder than expected. If you've poured almost all your off-world effort into Mars, and those problems turn out to be showstoppers or extremely expensive to fix, you're stuck. You either double down on a bad hand or accept a massive setback. If instead you push Titan in parallel or even first, you're spreading your bets. You develop one colony in a nitrogen, methane, deep cold environment with thick air, and another later in a thin air, dusty, moderate cold environment. Two different biospheres to study, two different climate systems, two completely different engineering stacks. If something about Mars turns sour, you still have Titan running, and vice versa. That's real resilience. A multi-planet civilization doesn't come from perfecting one single world, it comes from handling many radically different ones. Titan is the most different habitable niche we can realistically reach with near-future tech. By mastering it, you get maximum information and maximum robustness for every dollar, every launch, every engineer you train. But all this leads to the final pressure point. If Titan wins on survival physics, on long-term health, on industry, on science, on system-wide strategy, and even holds its own on economics and risk, what does that say about the way we've been framing Mars in the first place, and what does an honest Titan before Mars verdict actually look like when you lay all the numbers side by side? So after everything we've walked through, where does the score actually land, Titan or Mars? Add up the physics first, no hand-waving. Titan gives you a thick 1.5 bar nitrogen atmosphere. Mars gives you a near vacuum at well under 1% of Earth's pressure. Titan gives you low gravity, about 0.14 g that helps construction, lifting and launches. Mars gives you moderate gravity, about 0.38 g that still makes everything heavy without fully proving it's better for health. Titan's atmosphere and distance / radiation to near Earth or even below Earth surface levels with modest extra shielding. Mars batters you with a constant cosmic ray and solar particle assault unless you bury yourself under meters of regolith. Titan surrounds you with oceans and skies full of hydrocarbons and a surface made of water ice. Mars gives you thin CO2 air, patchy ice, and toxic dust. The only big win Mars has is distance. It's closer, so trip times and launch windows look nicer on a mission chart. But distance mostly hurts schedules and upfront cost. Bad physics hurts everything, day after day, for as long as people live there. If you optimize for long-term survival and growth instead of short, flashy wins, Titan's physical environment is simply more helpful. The hard truth is, closer is not the same as better, and once you stop treating time to arrival as the only metric, Titan starts pulling ahead on almost every survival and industrial parameter that actually matters. That leads straight into how your technology stack grows, because the first world you tackle shapes everything you build afterward. So what does your tech learning curve look like on each path? Go Titan first, and you are forced from day one into serious systems. You have to master compact, reliable nuclear power, because solar is weak. You have to nail closed-loop life support because resupply is slow. You have to get cryogenic engineering right, or nothing outside your hab survives -179 Celsius. You must have autonomous robots and software, because communication delays are too long for hand-holding. You learn aerial operations in dense, cold air, because flight is your best way to move fast on that world. Every one of those capabilities ports straight to other targets. Nuclear power and autonomy make the Moon and Mars easier. Cryogenic and deep cold hardware make Europa, Enceladus and Kuiper Belt objects possible. Flight tech helps anywhere with atmosphere. One staircase trains you for the whole outer system. Go Mars first and your focus narrows. You spend huge effort on dust-proofing, thin air entry and landing, solar plus backup power and fine-tuning agriculture in Martian soil. Useful, yes, but highly specific. You still haven't forced yourself to master deep cold operations, dense air flight, or extreme autonomy in multi-hour communication delay regimes. One path makes you a generalist, the other makes you a local specialist. Then there's the science payoff, which world actually blows our understanding of life and climate wide open. Mars offers an ancient record of water and maybe life. Old lake beds, dried up river channels, minerals that formed in liquid water, possible fossils or biosignatures buried in rock and ice. That's huge, but it's mainly about the past and mainly about one version of habitability we already know. Warm, wet, Earth-like conditions that then faded. Titan gives you a running methane weather cycle right now, with clouds, rain, rivers and lakes, just in a different fluid. It gives you a frozen analogue of early Earth's atmosphere, with thick nitrogen, methane, and complex organic haze. It very likely holds a subsurface ocean of liquid water with unknown chemistry and maybe totally alien forms of life or pre-life. Its surface is layered with prebiotic organics, tholins and related compounds, falling out of the sky every day. Studying that forces you to widen your definition of habitable and lifelike in a way Mars never will. If your goal is maximum disruption of old assumptions, the kind of science that rewrites textbooks, Titan is the larger jackpot. And this doesn't mean walking away from Mars. It means treating Mars with the level of respect it deserves. So how does Titan first actually protect Mars instead of sidelining it? If you rush big human bases to Mars now, you start contaminating its surface biology record immediately. Earth microbes ride in on every shipment, every leak, every footprint. The more you build, the harder it gets to tell which signals are native and which are imported. By going Titan first, you buy yourself decades to do Mars right. You can fly more orbiters, more landers, and cleaner drills. You can perform sample return missions, bringing carefully chosen rocks and ice back to Earth labs under strict conditions. You map the planet in detail, you take cores from deep subsurface ice, you look for life or its remains with as little interference as possible. When humans finally show up to build permanent Martian cities, they won't be guessing what they're erasing. They'll come from a civilization that already knows how to run sealed ecologies in a harsh place, that already understands planetary protection from hard experience on Titan. Mars gets a better scientific reading before it is changed forever. Put all of that together, and the storyline you've been fed starts to look small. It's always red dust, thin sky, lone habitat dome. What happens if you flip that script? Picture the first true off-world city not on a sun-blasted desert, but under a dim orange sky, at 1.5 bars, in air that blocks radiation. Its power comes from quiet fission reactors humming under ice, pumping heat and electricity through a network of tunnels and domes. Outside, lakes of methane and ethane stretch for hundreds of kilometers, hundreds of miles, with aircraft and drones cruising low and slow through thick, low-gravity air, moving people and cargo between outposts. Inside, labs are running long-term origin of life experiments with Titan air and Titan liquids, while factories turn atmospheric nitrogen and hydrocarbons into plastics, fuel, fertilizer, and structural materials. From that city, you send missions outward to other Saturnian moons, to Uranus, Neptune, and the Kuiper Belt, launched on cheap rockets from low gravity with locally made propellant. Later, you send missions inward to Mars and the asteroid belt, not as desperate pioneers trying everything for the first time, but as a mature outer system civilization extending its reach. That's the core of the argument. We need a base on Titan before Mars, not because Mars is unimportant, but because Titan is the training ground that makes everything else, including Mars, actually sustainable. Titan gives you the physics advantage, the technology staircase, the scientific jackpot, and the time to treat Mars like the precious record it is. Start there, and you become the kind of species that can handle both worlds, and then every other solid world after them, instead of betting everything on the one place that looks familiar, but quietly fights you on almost every front. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.